Okay, hi everybody. Welcome to April 1st, your second day of official e-learning. So, what we're doing today is kind of a continuation of what we did last time. So, we're kind of now jumping more into that part where we're going to design a lab that will produce a linear graph to determine the density of hand sanitizer. So, we kind of talked yesterday, we're going to be given these known masses, these known volumes. All that we know is that they're going to sink, and we want to use that idea where we can measure the distance, we can measure time to figure out what is the density of this liquid. So it's kind of a challenge. We want to be able to do it with a linear graph. So in order to do that, I kind of just gave you a little preview about what we're looking at. I really quickly want to review static fluids. Like it's been a while. It's been since September and August since we talked about fluids that were static, so kind of stationary situations. So where we talked about pressure, density, and buoyancy. And then I'll catch you free and I'll say, hey, try out this Google form. And I'll make a little video key to what I did in my experiment. So then you can kind of, after you do yours, you can check against mine and see, hey, how do those ideas, how do those sync up? So then what's going to be due for you is turning in that mystery fluid lab and then checking your ideas against the key. And I'll kind of look at some solutions too. And then maybe I'll do the experiment. I don't want to waste hand sanitizer because I don't want to put coins in it. But I'll figure something out. Maybe I'll do it with like water or something, and I'll do your experiment. We'll see what happens. So we're going to be looking first at this case of static fluids. I just want to review everything. So static is when we weren't flowing. Eventually, we got to those points where we had the pipes and we had those Bernoulli's equations, and we said, oh, if the pressure's over here in the whatever A1, V1, all those kind of good things. So first, we're just looking at static fluids, so fluids that are just staying still, like this cup of water. So the very first thing that we talked about when we did static fluids was density. And pretty much density is just this idea. Matter has this property called density. It's really your mass per volume. So how much mass do you have contained in some volume? And really the important part about density is that it helps us think about this particle nature of matter. So we think about the particle alignment of matter, and really quickly, we just have this equation for it. Density, that rho, is equal to mass per volume. So we see, okay, the denser an object is, it will sink, it'll kind of settle up below everything. And really it helps us think about, hey, everything is made up of particles. So on the left, we have this object that is more dense than the object on the right. It has more particles in this volume. It's more densely packed, so it's going to have more mass per that same contained amount of volume. So we're thinking about this idea of density, and it helps us think, hey, everything is made up of particles. Everything is made up of particles. And in fluids, which is what we're looking at here, so both gases and liquids, those particles are more freely flowing. They're able to flow, they're able to move around. In gases, they're a little bit freer, but both of them are able to move around and both of them are able to flow. That's why we call them fluids. So we're thinking everything is made up of these particles, and in fluids, the arrangement of these particles and the way that they're allowed to move is really important. So when we're looking at particles, one of the main ideas, one of the easiest ways to think about it, is we can think about them as just little tiny balls that are bouncing around, like when we thought about balls in previous physics classes. So we've taken previous physics classes and we've talked about momentum a lot, and we know that objects, they collide with walls, and there's this idea of impulse, and we've dealt with that when we said, oh, well, a ball collides with a wall and it turns directions and it changes directions, it applies some force, has this change in momentum, there's this impulse. So we've dealt with dealing with little bouncing balls in class before. Now what we're looking at is cases where we have a lot of them. So yeah, so just think about, hey, if somebody threw a ball at you, you would feel force, right? It would hurt, you'd feel that force. So that's kind of what we're looking at here. Is okay, if we have a ball and it's heading towards a wall, a force is applied on it, and that force changes its momentum. It applies an impulse to that object, right? It applies this change in momentum. So when we're thinking about pressure, instead of thinking about each individual force acting against the surface, instead of thinking about one ball, right? It would be a lot if we thought about every single particle hitting. So we're thinking about particles as the balls, and we know that every fluid is made up of many, many, many particles, so much that we can't count. So instead of thinking about each individual force that each individual particle is imparting when it hits that wall, we want to think about the bulk of it. So we want to think of, instead of just each individual force acting on the surface, we want to look at all of it. So we have to define this term of pressure. So this pressure is our force over some amount of area, over this area that the particles are acting on. So this is just going to help us out because instead of looking at each individual force, like each individual ball hitting the wall, we're able to think about each collision as a whole. So each force acting overall as a whole. So there's different ways that we can change the amount of pressure. If we have more collisions, if we have more balls hitting the wall, we have greater pressure. So there's different ways that we can change the amount of collisions or change the force in these collisions. We can either make the particles faster by changing the temperature, have more particles, decrease the volume, and we'll get to that in a little bit. So this is kind of looking forward, looking at our thermodynamics, but so just kind of tying those ideas together. And then when we were dealing with pressure, one thing that we did was we did a little lab where we checked the pressure at different elevations using an app on our phone. We just had this idea that if we have more particles, we have more pressure. So keeping that idea in mind, we did this lab and we saw, okay, as the height increased, the pressure decreased because there was less particles to supply that force. Over here in this corner, I have this picture, and I think it does a good job of thinking, hey, these air molecules are pretty light. They're able to go wherever they want. Yes, gravity's acting on them, but they're kind of able to flow around. But so more towards the surface, we have more air particles being pushed down. They're more towards the surface of the Earth because of that gravitational force. They're kind of able to stack up and stack up and stack up. And then we have a few that are more free, and they're feeling there's less pressure up here because they're less trapped by the particles above it, and they're just further away from that Earth's surface. So the gravitational force is a little bit less. So pretty much that's the main idea. As the height is increasing, the pressure is decreasing because there's less particles to supply that force. There's less particles actually acting on it, and there's also less weight of that actual column of particles above it. And then when we were defining pressure, there was two terms that were kind of confusing. We have gauge pressure, which is the pressure that a pressure gauge would read. We'll get to that more in a second. So it's really just ignoring the effects of atmospheric pressure. And then absolute pressure is the total pressure referenced to a vacuum. So we'll come back to this in a second. I just have a little analogy to help us out with that. So here's a little picture again. We'll come back to it in a second. So I like to think about this like if I'm driving my car and I have my speedometer going, my speedometer, if I'm driving, let's say 25 miles per hour, my speedometer, my gauge for speed will read out and say I'm moving 25 miles per hour. If I wanted to know my absolute speed, from my speedometer, it would say, oh, you're moving 25 miles per hour plus 1,000 miles per hour because that's about the speed that the Earth is moving. So knowing that I'm going 1,025 miles per hour is not helpful, especially because everything around me is moving at 1,000 miles per hour if we picture everything moving on the Earth together. So the gauge pressure just gives us a more readable number. Instead of saying, oh, you have absolute pressure, let's go back to this picture. Instead of saying you have absolute pressure plus some amount, plus some added pressure from whatever we're doing, the gauge pressure just tells us, oh, how much pressure do you have? And we know there's atmospheric pressure all around us, whatever, let's not worry about it. Let's just say, hey, how different are we from atmospheric pressure? So I think this picture is kind of nice because it helps us see, okay, absolute pressure is telling us, hey, based on vacuum, based on zero, how much total pressure is there? And gauge pressure is just, okay, let's get rid of atmospheric pressure. Let's not think about it. We know it's there. How different are we from atmospheric pressure? Get that analogy going. Okay, and then so we're saying this pressure is caused, and it's based on this height. So at any height, we have the some amount of particles that are above us. We saw that picture before, that the little dude had all those particles stacked above him. So we know that there's some amount of particles that are stacked above us at some height. And one of the main ideas, one of the main weird things we have to think about when we're dealing with fluids is that if we're at the same height, we're going to have the same pressure. We're going to assume, again, yes, there's some temperature issues here in the real world, but we're just going to say if we're at some height and we have some amount of fluid stacked above us, if we have that same amount of height of fluid above us, then we're going to have the same amount of pressure. So if we have the same height of column of air or water or anything above us, we're going to feel the same pressure from those, the weight of that above us, the pressure of that above us. This is a big idea because the same idea is going to apply for liquids, because liquids are a fluid. It's just a little bit harder to conceptualize. So this is a question that we had a few times, and it's a little bit weird because it doesn't feel right. But if we're looking at these different containers, if we have container A, B, C, and D, we're kind of labeling a location that is at the same height throughout all of them. And this question is saying, okay, which one of these has the lowest pressure? And they're actually, because they're all at the same height, they all have the same, or they're at the same depth, I should be saying. They're at the same depth, they have the same height of water above them. So all of them are at the same depth, which means that same height of water is above them. That's kind of pushing down on them, supplying that pressure from all of those little particles colliding. So that's each one is supporting that weight of water above it. So these are all going to be at the same pressure. And yes, we have some weirdness of the shape of the container, but really what that boils down to is the shape of the container is also supplying a force, and it's kind of counteracting. Everywhere is canceling. There's some weirdness with that. We don't really have to know why that's happening. We just have to know overall there's that height of liquid above it, there's that height of fluid above it, so it's applying that pressure. We just said that. So when we have this difference in depth, or we have this different height of air or fluid above us, a lot of big ideas come out of that. So we want to talk really quickly about why does this pressure difference matter? So the reason it matters is this idea of buoyancy. So we said that buoyancy is kind of this force that is applicable when an object is in a fluid. When we're in like the air, this buoyant force isn't so great. But when we're in liquid or something, you feel it. Like if you've ever been in a pool, you feel a lot lighter. You feel some sort of upwards force that's pushing on you. So that force is buoyancy, and it comes along because of this idea that there is a difference of pressure at different heights, at different depths. So if we have this cube, this is kind of us deriving this idea of density, or not density, sorry, buoyancy. So if we have this cube, let's say it has this volume that's the area times the height of this cube. So the area times the height, where the height is just right here, and our area is the area of this surface. So our volume is our area times our height. And then this next slide is kind of a lot. But so we said before that if we're at different heights, if we have different heights of fluid above us, if we're at different depths, then there's going to be different pressures. So this top face, I'm going to call it surface 1, is going to be at a lower pressure than this bottom face, this pressure 2, because it has a lower, surface 1 has less particles pushing down on it. Surface 2 over here, it says, hey, we have a big column of fluid above us, we have a lot of pressure from that, and then the pressure throughout this height is going to be the same. So yeah, it doesn't seem like there's anything pushing down on it, but it's at the same height as everything at this H2, which means that it's going to feel the same amount of pressure. So we can do some calculations and say, okay, at P1, at the surface 1, the pressure at this first surface is equal to our gauge pressure plus the density of our liquid, G times H1, so the depth that that's at. And we can do the same thing for P2. And then we can say, well, there's some sort of pressure difference there. We're thinking about pressure as a force. We see, oh, we kind of have this differential. We have a lower pressure on top, and we have a larger pressure on bottom. So we're going to feel this push. We're going to feel this push, this change in pressure, because we have different amounts of force. So if we take any object and you say, okay, I'm going to apply a lower force over that area on the top and a greater force over that area on the bottom, we'll feel this difference. We'll feel this upwards overall push. So we can figure out mathematically this change in pressure. So we get density of the liquid G times the H2 minus density of the liquid G times H1. And then when we do a little bit of math, a little bit of rearranging, we get this rho L, so density of the liquid, times G, H2 minus H1. And what we can really say is this H2 minus H1 is just really the height of our cube. And then we can redefine this a little bit. We said that pressure is force divided by area. We said then force over area is equal to this density of our liquid, G times H. And then if we rearrange that a little bit, we say A times H is just equal to our volume, the volume of that cube. So what we're going to say then is this force that's applied because of this pressure difference, this buoyant force, is equal to the density of our liquid, G times H times A, which is just equal to the volume of our cube. So we have this equation for buoyancy. All right, and then one other way that we could think about our equation for buoyancy, that's one way that we can do it. I think a little bit more of an intuitive way is to say, well, we have, instead of thinking about our cube, let's think about some amount of water. So before we put the cube in, if we're looking on this right side, let's picture this dark blue as just kind of like a highlighted piece of water. We're saying that at this location where the cube eventually settles out, if we're thinking about putting our cube in there, there's some volume of water. There's some block of water in here. And this block of water has this downwards force acting on it. And we know, for the most part, when we have water in a cup, it just kind of settles out. It's not constantly flowing up and down. It just settles out. So we're saying, okay, there's this cube of water, and we have some amount of water below it supporting it. So this cube of water, we can think about it like we've done before. Cubes are going to supply a gravitational force. So we can think about this cube has this downwards gravitational force. And the water below it, because it's not moving, it's in this static equilibrium, is applying this upwards force. Because again, we say, hey, when we have a cup of water, it's not moving. So there's this downwards force, Fg, that's equal to this upwards force, I'm just calling it F up, that's acting on the cube of water. Then, when we take away, when we put the cube in there, when we say, okay, well, before it was supporting this, the water was pushing up with this upwards force that was equal to the weight of the water. Now let's picture us putting our cube in there, and the upwards force is still going to be the same. The water get used to pushing up with this amount of upwards force. So when we put the cube in, we'll see it will feel the same upwards force. So if we want to figure out the amount of upwards force, we say, oh, well, the water had some sort of gravitational force, mass of that cube of water times g. And that's how much our downwards force was, which is also how much our upwards force was. And if we kind of rearrange that a little bit, then we can replace it. The density is equal to mass over volume. So we can say this Fg equals density times volume times g, which is also equal to our F up, which is also going to equal our equation for buoyancy. So that's just another way to think about it, saying, hey, the water was able to support this F up. It was doing that. When we put a cube in there, when we put some other object in there, it's still going to be pushing with that same F up. And that's just us deriving this equation for the F up. And then finally, so yes, we got this buoyant force. This is our equation. The buoyant force is equal to rho v times g. And the buoyant force is a little bit confusing because of the terms in there, because of the variables. So it's a force just like our other forces. That density, that rho in there, is the density of our fluid. So it's not the density of our object, it's the density of the fluid. It depends on the volume of the object that's submerged. So if you have a situation where half of your object is submerged, you're only going to use half the volume. So how much volume is submerged? And then g is just good old g. And then so buoyancy is always going to act upwards. And you can draw the buoyant force on a force diagram, just like you did before. And we can include it when we want to figure out the acceleration of an object in an F net equals mass times acceleration equation. So if we're just kind of looking at some situations with buoyancy, we have situations where an object will sink downwards. So where the buoyant force, if we look at our force diagrams, the buoyant force is less than our gravitational force. So we have this net negative acceleration. Our object will accelerate downwards. We have this situation where we put it in and it just kind of stays there. So we're saying we have this buoyant force is equal to our gravitational force. And then this other case where our buoyant force is greater than our gravitational force, and our object will accelerate upwards and it will float. So that's kind of just a brief review of the first part of the first unit that we did. Now we're going to move on and try out designing an experiment, but hopefully that was an okay review of everything that we did.